just a picture of the new design for the chamber. So basically, the big difference with this chamber versus the other chamber is that the crystal would be almost completely stationary, and it would be at that point. And so it would be connected to the manipulator, which is in this tube right here. But the point of this whole design is that almost all of these different ports are pointing directly at the crystal, and so you wouldn't have to rotate it, for example, to go between the doser and the mass spectrometer, that they would all be facing it at all times. And so basically the main features of it, this is the mass spectrometer, which is pointing directly at the crystal. And then we have 4 different ports for an electron gun, an ion gun, a UV source, and an extra one in case they want another one. So just in case. And those are all pointing in at angles here, 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 and here. And then there's also 2 ports that are specifically angled for an IR, so that they would be at the right angle. And then we have an oxygen doser, a sample doser, and then several extra ports, view ports, and whatever else.
So a forward-thinking chamber.
And I think that we might be changing it from how it is right now. Because Chris wants to put mu metal in the chamber so that we wouldn't have a problem with electric fields messing with the electron beam inside the chamber. And so to do that, we have to do something down here because there needs to be a big enough opening to coat the inside of the chamber. So it will probably end up looking different from this, but in general it will be how it is now.
When is this getting done? Like coming to life?
When it is made, I don't really know. Yeah.
So besides the crystals going to be stationary, what kind of electron gun are we going to use? Because for the current electron gun, it's like giving up electrons even when we're doing black experiment.
Yeah.
So if you're doing a black experiment, isn't it going to affect it?
Sorry, I didn't understand that. The current electron gun is...
Like, emissive electrons, right? So when we're doing the current one, the one that you did over time, low.
Oh, you can put a negative voltage on the crystal and stop all the electrons from hitting.
Sorry.
Yeah.
It actually has a purpose.
Sometimes, physics sometimes works, you know?
At least in the middle.
What they're talking about.
That's done?
Unless anyone has more questions.
Yeah. Is there anything we have to turn the crystal for, or is it all completely?
It would just be slight adjustments occasionally, right?
Yeah.
So we do need a manipulator, but we're not likely to be using it.
It's not like many degrees
Single-
every time you do an experiment.
I think we're first initially we're going to put the same manipulator sample holder
Right,
and
and,
then
just,
duplicate.
and figure out the optimal positioning and then
And plus we're not going to have money to buy the liquid helium cryostat initially.
right.
So we're just
Oh,
going to, sorry.
So you're gonna have to do you're gonna have to have the manipulator through the helium cryostat whenever you get that anyhow, basically.
Yeah, so that'll be a whole different thing, but we'll have something like the Mac tilt
Yeah.
on the new electron gun.
Oh, nice. So
You can just move things around a little bit. Not this manipulator that we have can position a crystal to 0.0001 inch accuracy. Okay, we don't need that going forward. Other questions?
Do you have program on there where the crystal is right now? Like inside?
That's just, that would be this point right here. The actual apparatus will be presented in this drawing, but that point is where everything converges.
Okay.
Oh, did they move?
Any other?
Good job, Kathryn. She just found out literally.
After I walked in. Oh, I'm sorry.
Okay, and I'm going to say a few more words, and then I'm going to turn it over to to Esther here. Esther is going to show you some of the data that we have collected. So Esther has many reasons why she wants to study ammonia. There are other reasons besides the reason Esther has. It turns out that ammonia was the first polyatomic molecule detected in space. First polyatomic molecule detected in space, and that was detected in 1968. It is thought to be a constituent of the atmospheres of the giant planets Jupiter, Saturn, Uranus, and Neptune. In the past, it is thought to have been part of the atmosphere of Titan, which is a satellite of Saturn that is very, very interesting to astronomers because Titan has an atmosphere that is closest to the Earth's in terms of the density of gases. They just sent this Huygens probe down to the Titan surface, and they found a lot of nitrogen, and they think that the nitrogen came originally from the ammonia that was there before. In addition, if you look at the interstellar medium, you look at the ices in the interstellar medium, about 5 to 30% of the water ices is actually ammonia. So the ratio of ammonia to water in these ices is about 3 to 10. So it's almost as high as methanol. I think after water, I don't know if hydrogen H2 is found in the ices.
Carbon monoxide.
Carbon monoxide is there, and H2.
I would where it goes in more CO than anything.
CO, okay, yeah, CO, definitely CO is there. So, water, H2, CO, methanol, and ammonia are probably the 5 most important species in the interstellar medium ices. So, we're already working, we have spent 2 years looking at methanol, and we just started looking at ammonia. Okay, I want to just briefly talk about the different types of experiments and make sure that everybody understands what we're doing here. There are 2 types of experiments one can do when you're talking about electron-induced reactions in the condensed phase. Okay, condensed phase means it's either liquid or solid. We don't have the facilities to do gas phase experiments. All of our experiments are in the condensed phase. So the first one is ESD, electron stimulated desorption. So what you have is a crystal, you grow a thin film, you irradiate with electrons, and what can come out are neutrals. Okay, we actually did these experiments in 1995 when we were using the UTI mass spec as both as a source of electrons as well as a mass spectrometer. So we could do ESD experiments with that old mass spectrometer because that mass spectrometer spewed out a lot of electrons out of the mass spec. So we could use the mass spectrometer as our electron gun. But this mass spectrometer that we have is a very good mass spectrometer, which means that it doesn't spew out electrons, which means that we cannot do ESD with this mass spectrometer, which was disappointing when we found that out in 2005. So what are the neutrals that could be coming off when we're irradiating ammonia? You could have just ammonia coming off. You could have N2 coming off. You could have H2 coming off. You could have NH2 radicals coming off. These are all possibilities. You could have positive ions coming off. Okay, one example would be NH4 plus. Okay, then of course negative ions coming off. The people in Canada have spent, about 30 years looking at negative ions coming off thin films. And they have found a lot of information about how electrons interact with condensed phase molecules. So in our case, with ammonia, we could think about H minus coming off, H minus. We could think about NH2 minus. And our mass spectrometer is capable of monitoring neutrals, positives, and negatives in a single experiment. But so far, we've been able to monitor only one species at a time. We've never tried to monitor all three at the same time. Okay, so for this experiment, on the y-axis is the mass spec signal, and on the x-axis is the electron energy. Okay, so there are two different instruments whose data we need to put in to get this graph. So Farah has been spending the last 1 month working on trying to get that to work properly. And we're almost there. That email that I just got an hour ago from Kimball Physics, I think is very encouraging, and tomorrow we may have the solution. Okay, but for now, what we're doing is we are now monitoring the mass spec signal as a function of time, knowing that the electron gun is changing the energy. But there is a discrepancy right now. So if you look at the mass spec signal as a function of electron energy, at low energies you should see resonances, and then it should go up. So basically you should be seeing a red curve like this red curve here. Okay? So the second type of experiment is post-irradiation. Okay? As far as I know, the first post-irradiation experiments relevant to low-energy electron-induced chemistry was done in our lab in 1995. It was a pure accident. Okay? So the experiments can be TPD, and now we have IRAS. The problem with TPD is that you have to heat the thin film to monitor the radiolysis products. So you're not sure if that heating process causes the radicals to come together, the radicals that you're forming in one of these processes. So the criticism that has always been leveled against my technique, our technique, is that we don't know whether they are nascent radiolysis products. And now Crystal has been able to use infrared spectroscopy to show that ethylene glycol, which is the major radiolysis product of methanol, is indeed formed at 100 Kelvin, no need to heat up. And she's identified several other products at 100 Kelvin without the need for heating up. So we're going to use all of these techniques to study the interaction of electrons with ammonia. And Kathryn and Megan have been collecting a lot of papers on ammonia, and it's surprising, not much has been done. One of my favorite sayings is that a diatomic molecule is a molecule with one too many atoms. Okay? That's the perspective I had when I came here to Wellesley College, because I spent my entire PhD banging xenon atoms on a platinum surface. Okay? So for me, a diatomic molecule was huge. Methanol has turned out to be a real challenge because of how many different radiolysis products you can form. Ammonia seems to be a lot more to my liking because it's a simpler molecule, the number of products are limited. Why don't we start the food going, and then Esther is going to take over.